Particular example, we've been asked to graph the rational function y equals x divided by x squared minus 9. Now, I've factored the denominator in this case so that our function can now be expressed as y equals x divided by x plus 3 times x minus 3. The reason why I factored the denominator is so that I can see the vertical asymptotes and also discover the restrictions in the domain. So the first part of the question is to state the domain. As you know, you cannot divide by 0, so therefore x cannot be equal to 3 or negative 3 for this particular function. You could write that in set notation, but I've written it in interval notation, so my domain is that my x values go from negative infinity to negative 3 in union with negative 3 to 3 in union with 3 to infinity. Because squared brackets haven't been used with the negative 3 or the 3, we're not including those particular values in the domain. My x-intercept and y-intercept are exactly the same in this particular case. The y-intercept would be found by setting x equal to 0, and you would indeed get an answer of 0. The x-intercept would be found by setting y equal to 0 and solving for x. In the case of a rational function, you should be aware that all you have to do is set the numerator equal to 0, and therefore the overall expression will be equal to 0, and that will occur when an x value of 0 is used. The only exception to that rule is if you end up with an indeterminate form where you end up with 0 divided by 0, but that's only occurs on rare occasions. So we have our domain and our x-intercept and our y-intercept. The next thing we have to determine is the function odd, even, or neither. To be even, f of x has to equal f of negative x. So that's what I start by doing, finding the f of negative x. So every place in our function where we had an x, we replace it with a negative x. And we discovered that the f of negative x is equal to negative x divided by x squared minus 9. You can see that that's not equal to our original function f of x. So this function is not even. Well, if the function is odd, the f of x has to equal negative f of negative x. So we take our f of negative x that we just worked out and we multiply it by a negative 1. So negative f of negative x is equal to negative 1 times negative x divided by x squared minus 9. When I do that, I get x divided by x squared minus 9. So in this case, f of x is indeed equal to negative f of negative x. Therefore, the function is odd. The next thing we have to do is determine if any asymptotes occur. This requires that you think back to what you learned in pre-calculus regarding rational functions. You know that vertical asymptotes occur when the denominator is set equal to 0, and that will occur when x is equal to 3 or x is equal to negative 3 for this particular function. So there are two vertical asymptotes. The horizontal asymptote in this particular case will be y equals 0. The reason for that is that the numerator is of lower degree, because it's a linear expression, than the denominator, which is a quadratic expression. So when the numerator is of lower degree than the denominator, then my horizontal asymptote is at y equals 0. Now, you may be scratching your head a little bit and saying, wait a second, I've got a horizontal asymptote at y equals 0, yet my function has a y-intercept and x-intercept at 0, 0. How can my function be crossing my horizontal asymptote? Again, you have to go back and think about what you learned in pre-calculus. And we realized that this little shortcut that we use for calculating horizontal asymptotes actually relies on a limit as x approaches infinity and x approaches negative infinity. Therefore, a function in or around the origin may indeed cross the horizontal asymptote, because we're not looking at x values that are approaching infinity or negative infinity in that particular case.